Hello everyone. Today I want to help you understand eigenvectors and eigenvalues because they can be quite confusing if you've never done it before. So yeah, let's get into it. The idea of an eigenvector basically says that when I do a transformation on it, it just gets scaled. It doesn't actually transform. So that's the critical point. Learn it conceptually before you do the math because it's going to be really difficult. And just visually, imagine I have some basis v1, v2, right? It's 0, 1, and or it's 1, 0, v2, and 0, 1, v1. Okay, and imagine I do some shear transform. So we shift from this little blue region, right, of our vector space, and we kind of just shear it over to the right. Okay, imagine what happens to, say, this vector here. Okay, imagine this vector. Imagine what's happening to him. Well, and let's just call this some random vector alpha 1. So vector alpha 1. Well, what happens to vector alpha 1 is he's going to get pushed over to the right. Hopefully you can just kind of see that. And he'll map to here. Let's call him A1 prime. Is he getting transformed or is he getting scaled? Well, you'd say he's getting transformed, right? Because he's actually physically moving. He's not scaling. But let's take a vector, say something like this. Now, this is imaginary. I'm not saying that this is true or not, but we're gonna roll with it. Let's say we have some vector like this, which we're gonna call beta 1. Okay, that intersects 1, 1. Let's say we do the same transform on it. If this vector beta 1, if b1 is an eigenvector, then beta 1 prime is just some scalar multiple of beta. Okay? That should make sense, right? And lambda in this case being a scalar. And in fact, that's the case. If we were to scale this, we'd see it would go right through our, and the blue is just the projection of the red here in our initial pre-transform. We're going to see, if I could draw this right, that'd be great. Let's just say it scales 2 times. So here we have beta 1 prime, and we see this is in fact the case. It's just a scalar multiple, right? And this is an important idea. This will pop up many times in random applications that you might see, where you need a transform that doesn't actually transform specific vectors. In this case, we didn't want to transform beta 1. Beta 1 didn't get transformed with the transform that we did. It just got scaled. Okay, that in essence is an eigenvector in a nutshell. So how do we find, let's go through a couple of things. How do we find eigenvalues? And how do we find eigenvectors? Well, we first have to make a relationship to find eigenvalues. Let's start with finding the eigenvalues. How do we find an eigenvalue? And an eigenvalue is just the scalar of this. So in this case, beta 1 to beta 1 prime is about 2. So the eigenvalue would be 2. How can we find an eigenvalue? Well, what we do is we make the following statement. We say that the transform of some vector x in some space is equal to some scalar multiple of that same vector, right? Because that has to be true. If I'm transforming it and it's only scaling, well, then it's equal to some scalar multiple of some vector x. Okay, let's keep R2 here. So let's assume this is for R2. You could bring this into R3 or 4 or 5, whatever you need. But to find an value, all you have to do is subtract over the scalar term, and we need to add an I. I'll show you why. If we want to scale, right, if this is just some number, let's say 2 in our case, what we need to do to make it in matrix form is multiply it by I so that it keeps the same dimension as TA. And this will simply become lambda on the main diagonal, like that. All right, so, and we can factor out the vector, and we can set this equal to 0. Okay, this is a critically important way to find your eigenvalues. So what do? Well, this is TA is going to be some constant term if we're in R2, A, B, C, D, minus this scalar. This is indeed a scalar. Lambda, lambda, 0, 0, right? This is multiplying to our vector, x1, x2, and this is all equal to 0. Right? You can combine these, and specifically what we're going to do is say that, and this is going to help us, the determinant, if we take the determinant of both sides, the determinant of the 0 vector is 0, so we'll just simplify that. If we take the determinant of both sides, what am I doing here? Okay, here we go. If we take the determinant of both sides, you get something like this, and you're going to see you're going to have to do a lot of factoring. And in fact, you can find, you take the determinant. In this case, it would be A minus lambda times D minus lambda minus BC, okay, equals 0. And hopefully you can see you can if A, D, B, and C are defined, you can just solve for lambda, and it turns out this is a polynomial. You'll just do foiling like you did in algebra 2, algebra 1, pre-calculus, maybe even you did foiling in calculus, I know that, but that's how you find eigenvectors. I'm sorry, eigenvalues. Okay, and that's one bit that you need. But there's another part here, and that is finding what are the corresponding eigenvectors. And we're going to look at an example and see if you don't have the right eigenvector, your eigenvalues don't really work. Everything has to work here. You can't just assume stuff, and it gets nasty. There are specific eigenvectors, there are specific eigenvalues, and you can't make assumptions to find different ones. So let's go ahead and make an algorithm for finding. Let me change the color here so it's a little nicer. Finding eigenvectors. Well, what we need to do is find what's called the eigenspace. And this is actually quite easy. What we're going to do is we're going to find some lambda here. And lambda will equal, let's say, alpha and beta. It's typical, you'll find about like 2, 3, 4, whatever. Let's say lambda is alpha beta. Well, to find the eigenspace, you're going to find, again, with this identity, of course, the x vectors here. You're going to plug in the eigenvalue that you found up here, into this, so let's say alpha and beta goes here respectively, you're going to solve the system and find the solutions. This will give you a basis, right? So solve, get your basis. This is going to be your eigenspace, right? And I'll show you an example how to do this. This is a lot of words, not a lot of visual. Finding eigenvectors, find the eigenspace. To do that, take your eigenvalues, plug them into this relationship that we just derived, solve that system. All right, find the base, and sorry, these the x should be here for you math sticklers. I don't care because it's not, you know that. I'm just being big dumb Corbin. Find the basis that makes up your eigenspace, and those basis vectors are eigenvectors that are going to scale instead of transform. And I'm going to show you that in a second. Okay? All right. So let's go ahead and do an example just to show how all this works. Assume A to be 0, 0, negative 2, 1, 2, 1, 1, 0, 3. Okay, so this is the vector A, and what I want you to find is 1, the eigenvalues, and remember the eigenvalues is just how much we're scaling our eventual, what we're going to find, eigenvectors. You do the last part first. It's really weird. Find the eigenvalues, those scalars, and then find the specific eigenspaces, right? So find the solutions to the system, and then from that, find the basis or the eigenvectors, okay? So the eigenvectors are the actual vectors themselves that are not going to be thrown off course. Okay, and I'll work through this with you guys. All right, so we know that A times any vector x, or an eigenvector x, not any vector x, geez, is equal to lambda I and then what we're going to do is take lambda I minus A times a vector is going to be equal to 0, right? Remember, what we want to do is find the eigenvalues here. So we're going to take a determinant on both sides. And so what does this look like? Well, lambda times I is just going to be lambda, 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 minus A, which if I remember is 0, 0, negative 2, 1, 2, 1, and 1, 0, 3. Okay, which looks like that. See, it's not so scary when you write it all out. And that's equal to 0. Okay. So the determinant is lambda, 0, negative 2. I guess I should put that notation. Oops, sorry. Negative 1. Lambda minus 2, negative 1. Oh, I'm messing up again. Negative 1. 0, lambda minus 3. Alright, so that's your determinant, which I assume you know how to find a determinant. I hope you do. This is lambda, and then this is multiplied by lambda squared minus 5 lambda. I'm foiling these guys right now. Plus 6. Okay? And right, this doesn't work because it's 0. Then we subtract. We're doing this. So we're going to add 2. Lambda minus 2. Okay. I think that's right. Let me double check my work. You can get caught up if you are just being silly. Yep, that works. I'll leave it to you guys to show that if we solve, because this is equal to 0, and if we get it all out, you get, this is called an eigen polynomial. It's common when you're solving for eigenvalues. So lambda to the third minus 5 lambda squared plus 8 lambda minus 4 equals 0 is going to factor, and this is not easy to see. You have to do, I believe, synthetic division here, although I forget. You get this in your factored form, which says that lambda is 1 and lambda is 2. So you have two eigenvalues. You have an eigenvalue of 1 and an eigenvalue of 2. Well, it turns out that each eigenvalue gives you a different eigenspace. So we have to treat each separately. So for lambda equals 2, now we're finding the eigenspace. And these guys are our eigenvalues. All right. Okay, so for your eigenspace, sorry, I had to look at a text message there. We're going to take the eigenvalue and we're going to plug it into this here before we take to the determinant. We're going to plug it in here, right? That was kind of in our scheme that we talked about. So let's do that. So what we do is we put a diagonal of 2's, right? Because that's our eigen. Subtracted by 0, if I can remember this, 0, 0, negative 2, what is it, 1, 2, 1, 1, 0, 3. Okay, so if we take this here, right, this is by some vector x, which I don't even care to write out in matrix form, times some vector x equals, with the same dimension, 0. Okay, so let's simplify this. Well, this says 2, 0, negative 2, negative 1, 0, 2 minus 1 is 1, negative 1, 0, 2 minus 3, negative 1. Okay, so it looks something like this. And I'll just put it out in full form just so you guys can see. This is going to equal 0, of course, but I'm just going to simplify. Remember, we can do row reductions here, which makes it quite simple. We're going to, oh, did I do that right? Yeah, sorry, this is negative here. Notice these are the same, so one of them will cancel. 2, 0, negative 2, negative 1, 0, negative 1, 0, 0, 0. And notice we can do the same thing with the second row, with the first row. And let's see here, what did I do? Oh, sorry, I see what I did. This should not be negative 2. This should be positive 2. Right, makes sense. And we're going to get 1, 0, 1. You can hopefully show that this is true. 1 and then a bunch of zeros for x1, x2, and x3. Let's call, let's say x1 equals negative x3, which we'll say is negative t. Okay, let's call x3 equal to t, and x2 equal to s. All right? So the general solution for any x, so x1, x2, and x3 is simply equal to negative t. Oh, sorry, not flipped it. st, which we can factor out to give the solution of we get a set of basis vectors, which is 1, 1, 0, negative 1 here, plus s 0, 1, 0, and this forms the eigenspace. These are the basis vectors for all eigenvectors, okay? So the span has eigenvectors in it, and that span won't get transformed with the transform. Now, what we're going to do in a little demo is show this here, that this vector is indeed an eigenvector. And we're gonna, for time, we're gonna omit the fact that lambda 1 gives different eigenvectors. You'll get a different basis, but for this case, we're only gonna consider lambda 2. So lambda equals 2 gave us a basis for the eigenspace, which is a set of vectors negative 1, 0, 1, and 0, 1, 0. Now, I'm going to leave this to you as an exercise. Maybe that would be good practice, but you should find for your other eigenvalue. Remember, we found 2 eigenvalues. Found both 2 and 1. If you do 1, well, then you'll find the basis for that eigenspace is going to be, let's see here if I can find it. Oh, here it is. Jeez. Sorry, I had a different one in my head that I thought we got, but you're going to get 2, 1, 1. Okay? So we're gonna take specifically this vector out, and we're just gonna investigate it, right? Because in math, it's good to look at what you're doing and see if it's true. So let's take the vector negative 1, 0, 1, and our claim is that when TA is applied a transform, it is only scaled. Not moved. And I'm going to use moved very loosely here. Transformed, right? If it's a shear, it's not going to, if the space is sheared, right, if we consider R2 and we shear it, right, it's not going to undergo that kind of movement. It's just going to get scaled, okay? So in fact, I have a couple vectors here that will be important, but here's our vector, negative 1, 0, 1. All right, let's do the transform on it that we had, which in this case, oops, sorry, I don't want calligraphy pen, I just want pen. So we need to show that A times that vector x, that eigenvector, is just some scalar multiple lambda x, right? And in this case, we should find that it's 2 of x, right? Because eigenvalues tell you how much you're scaling. So we should find that when we multiply A times x, it's only 2 of x, okay? And in fact, I'm going to tell you now, that's what we're going to find. But let's show it, right? for the wow factor.
Corbin, it's 1:30.
I'm making a YouTube video right now. Can you give me a second? Okay. So let's show this matrix multiplication. It's nothing hard. Distractions, guys. When math wants you to stop, it tells you, but you must persevere. You cannot let people distract you. So let's see here. When we do this row, we're going to get -2. When we do this row times this column, we're going to get -1. Plus 1, we'll get 0. We do -1 plus 3, that's going to be 2. And if you notice, that's exactly 2 times x, our vector. And in fact, it looks like this. All right. So our eigenvector was just scaled 2 in the transform with it. And notice it's exactly 2. That's the eigenvalue itself. Okay, but now what I want to consider is let's take one that does not fit this criteria. So ax does not equal a scalar multiple specifically of 2x. And let's call x, I don't know, 1, 1, 1. Okay, we'll make it really easy to find. So ax in this case, which I'm not going to show really thoroughly, is going to be -2 5, right? Is that, so if it's 1, yep, that's, no, it's 4, geez, 4, 4. Okay, so ax is -2, 4, 4. And notice that's not 2 times our vector. So we expected if 1, 1, 1 is an eigenvector, we should have expected it to output 2, 2, 2. So this is expected, but we really didn't get that. We got this. So not an eigenvector. Okay, and let's just visualize that quick. And it looks like this. All right, so, and I'll make this one blue. So notice when we transformed it, and I'll put the initial vector in. Right, we wanted it to stay on the line here of 1, 1, 1, but it got shot off specifically into the -x direction, so it kind of like flipped over the xy or the zy plane and got scaled up that way. So it's not an eigenvector, and in essence, that's all eigenvectors are. You're finding transforms that just scale your vectors instead of doing crazy things to them, like, you know, reflecting them. So that's all on eigenvalues, eigenvectors, eigenspaces. Hope you have a wonderful day, guys. Bye-bye.